I'm not going to look to this guy, but I will consider the 8y and z. 8y and z, it means dividing on 2, it will be 4 in y and z, and the 4 in z and y. Half the value in y and z, and half the value in z and y. While the rest of the elements is going to equal to zeros, as you can see. So that's the matrix, I'm sorry, that we are dealing with. This is for x, y, and z. Okay, so it's supposed to be like this. I believe this matrix 1, 0, 1, 1, 0, 1, and that's 4 and 4. And okay, it contains a typo here. I believe this is x and y. So if this is x and y, you will have these two values equal to 2. So I'm sorry for this typo here. It's supposed to be x and y. Okay, now I can get the eigenvalues relative to this matrix. If you remember the characteristic equation, is really very simple. All I have to do is to get a minus lambda of I equal to 0, which means I will subtract lambda from the principal diagonal and evaluate the determinant of this matrix and put it equal to 0. If we try to do so, I will multiply 1 minus lambda times negative lambda times 1 minus lambda, then 2, 4 times 0, 4, 2 times 0, it will be equal to 0. This guy is going to equal to 0, minus 16 times 1 minus lambda, minus 4 times 1 minus lambda. Simplifying this equation, I will reach this guy. So now I have the lambda values, which are positive 1, negative 4, and positive 5. Now I have mixed values, negative 4, 1, and 5, for the eigenvalues. So I will have indefinite case for the classification of this matrix. And it really goes very well. It's direct. If you check triple 1, it will give you a positive value. If you check 0, negative 1, and 1, it will give you a value less than negative 7, which confirms the results that we have from this eigenvalue vector. Okay? So just remember, just to fix this guy, I will resend it to you shortly. Also, for this symmetric matrix, which have, this is the matrix, the symmetric one, with all these elements, I remark that the sum of the rows, if you remember the second session in eigenvalues, it's all equal to 2. So now I have one of the lambdas is equal to 2. Also, if you put negative lambda, 1 minus lambda, 1 minus lambda, this is going to be 0, that's going to be 0. Negative 1, and this is going to be 0. So also you will have lambda is equal to 0. It's very simple to analyze this equation. It's going to be direct. So I have the lambdas, which is negative 1 and 1 and 2. Then the quadratic form is also indefinite. I can write the equation of the quadratic form corresponding to this matrix, multiplying x, y, and z and x, y, and z. Or simply, I can write the coefficient 0 times x squared, so there is no x squared, 1 times y squared, plus 1 times z squared, then plus 2 of an xy, plus 2 of an xz. That's the quadratic form relative to this guy, in case if you want to evaluate this matrix. If I want to have a diagonalization for this matrix and making a change of variables, I can use lambda 1, lambda 2, lambda 3 in order to get my quadratic, change of variable in order to evaluate. Okay, so once more, as we can observe, by a q of x1, x2, x3, this is going to equal to q times v of y1, y2, y3, and it will leave you with this case. Also check for the errors that exist in this matrix. Now I will come to the exercises. He needs you to consider the quadratic form q from R2 into R defined by negative 5 x1 squared, 2 over x1, x2, minus 5 x2. I believe the symmetric matrix is really very simple to get. So it's going to be x1, x2, and then you will have your matrix here, x1 and x2. I will take negative 5, which is going to appear here in front of x1 squared, negative 5 also for x1, 2. Then I will divide the 2 on 2, putting half of it in 1, 2, and the other half in 2 and 1. That's my symmetric matrix. And he's asking you find the symmetric matrix A associated with the quadratic form and classify it using the minors of A. Now I can classify using the minor of, or the minors of this matrix, which is -1, 1, and the -5, according to the roots. If you remark, the first one of them is negative, and once you try to evaluate, it's gonna be a positive, so which leaves you with a negative definite matrix, as you would see. So once more, this is the matrix, that's the quadratic form, -5, -5, 1, and 1, as you can see. Very simple, I will get the delta 1, which is gonna be the value relative to -5, which is negative. Then evaluating 25 minus 1 is gonna be greater than 0, which leads you, according to our rule, okay, if you remember the rules, if delta 1 is greater than 0 and delta 2 is greater than 0, you'll have a positive definite. I thought to write you the relations. Delta 1 is less than 0, which in this case, and delta 2 is greater than 0, then you will have a negative definite. If delta 2 is less than 0, okay, then the quadratic form is indefinite. Of course, this is the case, the second one, so it's a negative definite case. For number B, he is asking you to confirm by finding the eigenvalues. It's very, very simple. All I have to do, even before to go to the next slide, I will have to evaluate the eigenvalues, which is gonna be -5 minus lambda, 1 and 1, -5 minus lambda equal to 0, and then I will expand this guy, okay, into a quadratic form. It's very, very simple. You will have, take negative as commons, so you will have 5 plus lambda to the power of 2 minus 1 equal to 0. Then start solving this equation as you will see in the coming slide. It's very, very simple, but lengthy steps, since this is an exercise, so it's not gonna be a big deal. So that's the matrix. As I told you, I've tried to expand it, and then trying to solve this quadratic form, you will have -6 and -4. Since you have the eigenvalues are negative, then your matrix or this quadratic form is a negative definite, which is exactly like the result that we had previously. Now, find the change of variable to eliminate the cross term. It's very, very simple. All I have to do is to get the eigenspace or the eigenvectors relative to -6 and -4. Then putting them into the matrix for a quick resolution. This is one, when you use -6, the homogeneous system will be -5 plus 6, -5 plus 6. So this is the coefficient matrix. Eliminating the first row times -1 and added on the last row, you will have the relation connecting the x and y. Y is equal to -x or vice versa. Substituting in the vector relative of the eigenvector relative to this value, you will have 1 and -1. This is V1. In a similar manner, for lambdas equal to -4, you will have 1 and 1. Now I can write the B matrix responsible about, that's the B matrix, responsible about the diagonalization as we talked previously. So it's going to be a 1 and the -1, 1 and 1 for the second vector. This matrix can be, okay, is a symmetric matrix. This is a symmetric matrix, which is going to lead to an orthogonal matrix. So the inverse of this matrix is its transpose, okay? But I will modelize it, so I will divide on the sum of the squares of these elements over 2, and this is exactly over 2. So the B matrix should be 1 over root 2, -1 over root 2. This guy is going to be 1 over root 2 and the 1 over root 2. This matrix, the inverse is the transpose. So B minus 1 is equal to the B transpose, which is, because it's an orthogonal matrix, so it's going to be simply 1 over root 2, -1 over root 2, 1 over root 2, 1 over root 2. Now I have the B matrix. If I want to get the diagonalization, it's going to be very, very simple. D is going to equal to B times the A matrix times B minus 1, and then you will have your matrix diagonalized by this form, -6, -4, and those are coupled zeros. So the new quadratic form on the elimination, after eliminating the mixed terms, it's gonna be a negative of an x, let's say of x squared, minus 4 of an y squared, and that's the quadratic form. We will go through these steps with the slides step by step. So once more, all I have to do after getting the vectors, as I told you, v1 and v2, I will put them all together in the matrix that I told you about. That's the first vector as the first column, the second eigenvector as the second column. I will divide each element of the first vector on its magnitude. So it will be divided on the root of first 1 square, then negative 1 to the power of 2, which is 1 square. I need to make this clear for you. So in order to get the magnitude of this vector, it's simply negative 1 to the power of 2 plus 1 to the power of 2. This is why it's root 2. And exactly the same here. It's just a chance. It happens as a case in this problem, but it's not generalized. So the first is going to be 1. The last is going to be 1, 2, 1 to the power of 2, 1 to the power of 2. So both of them is equal to 1 over root 2. And that's an orthogonal matrix, which means the inverse is its transpose. So now I have, that's the negative 6u1 squared, negative 4u squared. No cross terms, clear classification, and the q is a negative definite. You have another problem, which is almost exactly the same. So I can get also 1, 1, 2, and 2. That's the symmetric matrix. I can use this classification. He's asking you for the linear symmetric matrix of A, represent the quadratic form. Write the quadratic form associated with A squared. So all I have to do is to evaluate A squared. So multiplying A squared, it's gonna be 5, 4, and 4. So it's gonna be 5x squared, 5y squared, and the 8 of an xy. That's the quadratic form assigned to this guy, if I'm using xy or x1 and x2. Then check the eigenvalues of A squared, very simple. All I have to do is to have 5 minus lambda, 5 minus lambda, and then trying to evaluate this determinant exactly the same. So once more, those are the values. I can evaluate the values of this matrix for the eigenvalues, and it's gonna be equal to 0, so it's a positive definite for sure. That's the proof. That's for A equal to A squared. In all times you will have a positive definite, because if A is B times D times BT, and you are getting B squared, so you will multiply this guy times 2, you will have D to the power of 2, which means that you will be dealing with a positive definite in all times case. So it's a positive semi-definite. You don't have negative terms. Also, that's another problem with a 3 by 3. Also, I've solved it in details. Getting the vector V112 is an eigenvector. If you want to check, all you have to do is to multiply V times A. You will find the results equal to 0, so it's identified as an eigenvector. Okay, write the characteristic equation. I will subtract negative lambda from all the elements. I will simplify it. Now I have the values of lambdas, which is lambdas equal to 0 or lambdas equal to negative 6 with multiplicity equal to 2, so it's a repeated one. And we will have semi-definite case, and that's for the nullity of getting the rank of the eigenspace relative to negative 6. So the algebraic multiplicity, I want you to review this part, is equal to 2 in case of negative 6, and the geometric multiplicity is equal to 2 in this problem. Now the eigenvalues of A is equal to 1, and that's negative 6. So you can find easily that's the value of Q less than or equal to 0. It's a negative eigenvalues. As I told you, it's a negative semi-definite. For this problem, also is giving you, I want you to evaluate the quadratic values of 1, 3, and 0, and 2, 1, 1. All I have to do is to substitute by these values in this quadratic form and see the results. So if I made the substitutions, you will have negative 2 and 6. So you have an indefinite matrix. This is the matrix. If I want to evaluate lambdas also, I will be able to reach this cubic matrix, this cubic equation, I'm sorry. Solving it, we will give you the values of lambda, which is 2, 1, and the negative 2. Then 1, negative, 2 positive values, which is indefinite. Also, this problem, he wants you to classify each and every one of these quadratic forms. I've already did that for you. This is the how to classify them. Once more, I wanted to have it to review it with you, and then that's the classification. As I told you, I've solved this problem and I've sent you the solution, so you will be able to find it very easily. Thank you very much, and this is the end of our course with the quadratic forms. I want you to go through those slides, very good, and to try to resolve these problems. As I told you many times, I've already sent you the PDF. Please study well, because in the last period, you had the determinants properties, you had the eigenvalue and the eigenvectors evaluation, either by the characteristic equation and the regular steps, or by using the propositions that we already introduced in the second lecture of evaluation of eigenvalue and eigenvectors. Then we went through the dynamical system. For sure you will have a problem on this, and we already solved the assignment together, so you should be in a very good place. And this is for the quadratic forms. Guys, folks, I'm really very happy to be with you and to end this course with you. I will share some of the revision lectures with you later, inshallah. Thank you very much. Appreciate it. Appreciate the time, and appreciate that you are watching and trying to exercise as much as possible. Thank you very much. Thank you. Bye-bye.